Hello and welcome to another video about how to solve an interesting question using a Monte Carlo experiment. And the platform that I'm using is Pluto.jl, which is a notebook for Julia. So the question is the following. Suppose we have the unit circle, we draw n random chords independently, and we count how many of these chords intersect. And it's random chords, so we would like to know the expected value of the number of intersections. That's the question. Okay, so first of all, let's define what does it mean a random chord. So think about the unit circle, and a random chord basically defined by the 2 points on the circumference of the unit circle that are connected with a line, which is the chord. And basically what we need to do is to choose two random numbers independently, uniformly from the distribution, on the uniform distribution between 0 and 2 pi. Basically the radiant representation of those 2 points. And if you want the points in xy coordinates, using the cosine and sine, you can get them this way. So theta 1 and theta 2 drawn independently from the uniform distribution 0 to pi. Okay, so how many intersections there will be? So first of all, we need to figure out any pair of two random chords will intersect. What's the probability of that happening? Okay, so there is the analytical solution here, and I'm not going to go over it. The answer is 1/3, and the reason, kind of hand-waving reason for it, is that it can be on this side of what the second chord that we draw can be on this side of the first chord, on the other side, or the third option is that they intersect. That's a hand-waving explanation. So if we have n times n minus 1 over 2 pairs out of the n random chords that we drew, then times third, it's n times n minus 1 over 6. Okay, so the expected value is in this box. Okay, so let's, instead of thinking about the analytical solution, let's do a Monte Carlo experiment. Okay, so drawing a random chord, here is a unit circle, here is a random chord. I can press this button again and I'll get another chord and press it again. And so this is a very short chord, etc., etc. Okay, so what is the Monte Carlo experiment? We will draw n random chords. We'll do that many times, and each time that we draw n chords, we will check how many intersections. Okay, so we need to explain to ourselves what does it mean the two chords intersect. So the first chord is theta 1, theta 2, again drawn from the uniform 0 to pi distribution. And another chord is, we denote it by phi 1, phi 2, again drawn in the same way. So now suppose that we order these two pairs, and there is more description here, but in short, let's call A the minimum between theta 1 and theta 2, B is the maximum, the other point, and the two chords will intersect if either, but not both, phi 1 is between A and B, or phi 2 is between A and B, but not both of them. Okay, because then they are on the completely on the other side of the chord. Okay, so what we need to do again, loop over capital. Here is a function that will do that. Order the first pair, then look whether the second pair intersect it, and return true if they intersect, false if they don't. Okay, in Julia, this is the V with the under it's the exclusive OR, the XOR here. Julia accepts mathematical notations. Okay, the Monte Carlo experiment is very simple. Capital M is the number of Monte Carlo experiments, so we keep doing it capital M times, and each time we draw random chords, n of them, and we will check their intersection by calling the function that we defined above and getting true or false, counting how many times we get a true, and then eventually we accumulate all those intersections, divide by m, and the answer will be the expected value, or the Monte Carlo answer to what is the expected value. So here is an example of 10 random chords. Okay, analytically we know that it has to be 10 times 9 over 6, which is 15. The Monte Carlo that we ran here got us very close to 15. I can run it again. It will be rather quick, 14.997, etc., 76, and it's very accurate with 20,000 Monte Carlos. Okay, so this is a neat way to answer this puzzle or this question, sorry, and we verified that what we analytically computed is correct, and it is. Okay, as you can see, it ran very quickly. There is additional material here at the end of the notebook thinking about how to make the code run faster, because the order of operation is capital M times n squared. That's the order of number of operations. So it can be a big number, but as you could see, even on my laptop, it ran very, very quickly. So there is some discussion here about computational optimization, because Julia is compiling the code, so there are some consideration to think whether we should inline it and inbound and all those macros. I'm not going to discuss it in this video, but you can look at the GitHub page that I will put in the description and figure out what can help, and sometimes things that you think help do not really help, and some things, other things may help, and there is at the end a way here is this table that we could get 1.5 times faster, 3 times faster, and even 3.2 times faster, depending on the size of n, and that can be very substantial in other situations, so you can look at it. Thank you for watching. That is it for this time. See you next time.